Hello, this is Dr. Hanaa Assil, and this is Unit 3 of the Pearson Edexcel International AS Chemistry, and this was the paper that was in October 2022. The first question was, in the test for sulfate ions, an acid is added followed by aqueous barium chloride. Give a reason why the mixture needs to be acidified. Now, do you remember the test for sulfate? What was the test for sulfate? The test was for sulfate was I should add dilute hydrochloric acid and barium chloride solution, and I should get a white precipitate. So the question is, why do we need to add acid? You should remember that we add acid to remove any carbonate present, because if there is carbonate in the solution, then just adding barium chloride would give me a white precipitate even if I don't have a sulfate. So we remove any carbonate or any ions that may form a precipitate, and then we add the barium chloride. In that case, if I get white precipitate, then I have sulfate. Identify by name or formula a suitable acid and justify your answer. Of course, if I'm adding barium chloride, my acid should be hydrochloric acid or could be nitric acid, because these will not form a precipitate with barium ions. But if I put something like sulfuric acid, of course, sulfuric acid is an acid that has sulfate. So if I add it to barium, it would give me a precipitate. So hydrochloric or nitric acids are suitable because they will not form a precipitate with barium ions. A student is given a sample of white crystals to test for sulfate ions. So you have a solid. And he says, describe how the test should be carried out, including the positive result. Again, we said if I'm testing for sulfate, but I'm starting with a solid, so I have to add water and stir to dissolve the solid first. Then we add the dilute hydrochloric acid and barium chloride. In that case, I should get a white precipitate if the sulfate is present. A student is given a solid known to be either sodium bromide or barium chloride. State the test you would carry out on separate solid samples of sodium bromide and barium chloride to show the cations present. Of course, the cations are the metal ions. So you're actually being asked to write the test for sodium ions and barium ions. What is the test that we have? Of course, this is the flame test, and you should know that barium ions will give apple green flame, while sodium ions will give a yellow flame. So remember that this is the flame test. Barium gives green, sodium gives yellow. State the test you would carry out on separate solutions of sodium bromide and barium chloride to show the anions present. So now you need a test for bromide and chloride. What is the test for halides? We should add dilute nitric acid and silver nitrate solution. If I have bromide, it should give me a cream precipitate that dissolves in concentrated ammonia but not in dilute ammonia. If we have chloride, this should give me a white precipitate that dissolves in dilute ammonia. Okay? The second question says, some antacid medications to treat acid indigestion contain magnesium carbonate. A student investigates how much magnesium carbonate is in an antacid tablet. So what he did was crush a 1.3 grams tablet to form a powder, add the powder to a certain amount of sulfuric acid, stir the mixture until the reaction is complete, make up to 250 centimeter cubed with distilled water, and then titrate 25 centimeter sample of the solution against sodium hydroxide to determine the number of moles of sulfuric acid that did not react. So what is he doing? He has a tablet and he wants to know how much magnesium carbonate is in the tablet. He adds the tablet to sulfuric acid. Of course, the magnesium carbonate in the tablet will react with the acid. But then, how do I know how much acid has reacted? I go through a roundabout way in which I titrate whatever is left of the sulfuric acid so that I can determine how much sulfuric acid did not react. Then I subtract it from the original amount of sulfuric acid in order to know how much reacted with the magnesium carbonate. Are you following? So he did titrations, and these are the results, and he says complete the table. Of course, if I have final reading and initial reading, all I'm doing is final minus initial. So I subtracted each of these, 13.45 minus 0, 25.6 minus 13.45, and so on, to get the titer in each titration. Then he says calculate the mean titer. Now, when you look at these results, you will find that one of them is 13 point something, almost 13.5. The others are all 12.15, 12.25, 12.20. When we calculate the mean, we take only the concordant results. You remember what are concordant results? They are the results within 0.2 of each other. So the ones that are near to each other within 0.2, these are the ones from titration 1, 2, and 3. And this is what I use to get the average or the mean titer. So I add them up and divide by their number. There are 3 of them. I get a mean or average of 12.2 centimeter cubed. So this is the volume of the sodium hydroxide that reacted with the acid left after the reaction. The next question, part of the question says the equation for the titration is this. Calculate the number of moles of sulfuric acid that reacted with the sodium hydroxide in the mean titer. So we had a titer of sodium hydroxide. What did we say? We had the titer of the sodium hydroxide, which we calculated to be 12.2. And he gives me the concentration of sodium hydroxide, which is 0.025. So if I have concentration and volume, I can get the number of moles of sodium hydroxide that reacted. That is concentration times volume. Again, remember to divide the volume that was in centimeter cubed divided by 1,000 to get decimeter cubed. So this comes up with this number of moles of sodium hydroxide. When we look at the equation, we find that 2 moles of sodium hydroxide react with 1 mole of sulfuric acid, or the ratio of sodium hydroxide to sulfuric acid is a 2:1. That means that if I have a certain number of moles of sodium hydroxide, then in order to get the number of moles of acid, I should divide that by 2. So this gives me the number of moles of sulfuric acid that was left in the solution that I was able to titrate with the sodium hydroxide. Then he says calculate the total number of sulfuric acid used at the start of the experiment. If we go back, we find that he said he put the tablet into the solution of sulfuric acid 75 centimeter cubed of 0.2 mole per decimeter cubed. So from that, I can get the original number of moles of acid, concentration times volume. The volume is in decimeter cubed, and I get this original number of moles of acid. So this is what I started with. Remember that I started with this number of moles of acid, then some of it reacted with the carbonate in the tablet, and then I titrated what was left with the sodium hydroxide. So now he's saying calculate the percentage of magnesium carbonate in the antacid tablet. Okay, going back again, of course he says you must show all your working. So going back again, what did we say? We want the number of moles in 250, because what he did was he reacted the tablet with the acid, he got a certain amount of solution, and then he made it up to 250 and took 25 of that and titrated it with sodium hydroxide. So the number of moles that we calculated was number of moles in 25 centimeter cubed of acid. But I had a total of 250. So of course the total number of moles of acid that did not react is this amount, this total number of moles. Now, the number of moles of acid that reacted would be the difference between this and the original number of moles that we calculated from the 75 centimeter cubed and 0.2 mole per decimeter cubed of acid. Are we following? So this gives the number of moles of magnesium carbonate, because the equation says that the number of moles of magnesium carbonate should be the same as the number of moles of sulfuric acid. From the number of moles of magnesium carbonate, I can get the mass, and that means that the mass of magnesium carbonate that was in the tablet is 1.136. Then I can get the percentage, because he said that the original mass of the tablet was 1.30 grams. So if 1.136 of it is the magnesium carbonate, then I can divide that over the total times 100, and that gives me a percentage of 87.4%. I hope that was not too confusing to you. Okay. Give one possible reason for carrying out a rough titration. Remember that when we do titration, I have to do a rough titration first. That means I do a titration, but I really don't know where the end point is, so I could easily pass it. So we do a rough titration to determine the approximate end point, and then I know, for example, that I should have a certain volume. Then when I repeat the titration, I can be careful and get it more accurately. Phenolphthalein indicator was used in the titration. State the color change seen at the end point. So he added phenolphthalein to what? Remember, what he had in the flask, what he was titrating against sodium hydroxide, what was in the flask was the acid. So if you remember, the colors of phenolphthalein in acid are colorless, and then it changes to pink. So the end point in this case will be when the first pink color remains in the flask. This question says precipitation reactions can be used to determine the formula of compounds. A bottle has a turn label which shows that it contains nitrate with a formula of something NO3 twice. So what we're trying to do is we want to find what is X. A technician dissolved a sample of 12.41 gram of nitrate in deionized water to make 100 centimeter cubed of solution. Of course, you should remember deionized water is similar to distilled water. This is what we use in the lab for experiments, because it's pure water that does not have anything dissolved in it. So anyway, he made up 12.41 gram of the nitrate in 100 centimeter cubed of water. The technician pipetted 5 centimeter cubed of 1.5 mole per decimeter cubed of potassium iodide into a series of test tubes. So I have 5 centimeter cubed of 1.5 mole per decimeter cubed potassium iodide in each test tube. Now each test tube then had a certain volume of nitrate solution added to it. This formed a cloudy yellow solution. Remember that nitrate with iodide, this gave a yellow solution, and the precipitate was allowed to settle. The height of the precipitate was then measured. So the equation for the reaction he gives me is this. And he gives results of experiments in a table, and he says, plot the data on the grid. So when we have a graph like this, of course, the first thing we do is we need to label what is the x-axis and what is the y-axis. So the volume of X nitrate, whatever is on the left of the table, goes on the x-axis down, and the height of the precipitate will go on the y-axis, and then you plot the points in small x's and you join them. In this case, it's going to be joined with two straight lines that intersect. Then the question says, state why the height of the precipitate becomes approximately constant. Why is it that at the end the height is constant? Remember that we're adding nitrate solution to potassium iodide. As we add more and more nitrate, more and more of the iodide reacts. But at some point, all the iodide has reacted, and any more nitrate that we add would be excess. So the height at the end becomes constant because all the iodide has reacted, and the nitrate added is actually excess. So I cannot get any more precipitate. Determine the minimum volume of nitrate solution needed to react completely with 5 centimeter cubed. You must show your working on the graph. So from this graph, we had in the test tube, we had 5 centimeter cubed of potassium iodide. What was the volume of nitrate that we needed to make the maximum height of precipitation? Well, from the graph, that is where the two lines meet. So this graph actually says that when I added 10 centimeter cubed of the nitrate, that gave me the highest height of precipitate. I couldn't get any more precipitate. So this is the volume of nitrate needed to react with the potassium iodide. Calculate the number of moles of potassium iodide. Okay, what did he add? He added 5 centimeter cubed of 1.5 mole per decimeter cube potassium iodide. So we want to get number of moles. Number of moles is concentration times volume. Remember the volume, centimeter cubed, I divide by 1,000, so it's actually 0.005. And that gives me the number of moles of potassium iodide in each test. Now, calculate the concentration of the metal nitrate in grams per decimeter cube. So, I know from the top that I have 12.41 grams in 100 centimeter cube. So, the concentration in decimeter cubed would be the 12.41 over the 0.1, the mass over the volume, that is the concentration in gram per decimeter cubed. So this gives me a concentration of 124.1 gram in a decimeter cubed of solution. Now, he wants me to identify X. What is X? Using all the answers that we just found out. So, looking at the equation, we determine that the number of moles of the X nitrate should be half of what we got for the potassium iodide. The equation says 1 mole of nitrate reacts with 2 moles of potassium iodide. So the number of moles of the X nitrate is the number of moles of iodide over 2. And this is the number of moles of nitrate in the 10 centimeter cube that we got out from the graph. So the concentration in moles per decimeter cubed is this N over V. So this is 0.375 mole per decimeter cubed. Then I can use this mass that we got over the number of moles. We know that we have 124.1 grams. That's what we calculated in a decimeter cubed. And we just got that in a decimeter cubed, I have 0.375 moles. So mass over the number of moles, that will give me the MR. And then this MR is actually the total of the mass number of X plus nitrogen times 2 plus oxygen times 6. The total is the 330.9. And calculating for X, this gives me a mass number for the metal of 206.93. When I go to the periodic table and I look for which element has a mass of 207, I find that that is lead. So that means that X was lead. Deduce the ionic equation for the formation of Xi2. So we're trying to form lead iodide from lead ions and iodide ions. Remember that the lead ions are aqueous, iodide ions are aqueous, and you need to balance the equation. So this is the ionic equation for formation of lead iodide. Suggests why some of the precipitate heights may be above the maximum height expected. So sometimes we measure the height of the precipitate, but it's actually higher than what it should be. What do you think happened? Well, we should actually leave the precipitate to settle down before we measure the height. So if the height came out to be too high, that probably means that we did not give the precipitate enough time to allow it to settle down. So the precipitate was not left long enough to settle down. The metal nitrate is toxic. Draw the hazard symbol that should be displayed on the bottle. Do you remember the hazard symbols? You should be familiar with these hazard symbols. Which one is for toxic? And you should actually be familiar, for example, with the one for flammable and the one that says corrosive. So this is what you should draw in the symbol for toxic. Propane 1-ol, propane 2-ol, and 2-methyl propane 2-ol are all alcohols commonly used in school laboratories. Acidified potassium dichromate is used to oxidize alcohols. State the color change seen when an alcohol is oxidized with acidified potassium dichromate. Do you remember the color change for potassium dichromate? You should know that originally it is orange. When it reacts and acts as an oxidizing agent, it changes from orange to green. Draw a label diagram of the apparatus that is required to prepare and collect a sample of propanal by heating propane 1-ol with acidified potassium dichromate. You remember that when we oxidize a primary alcohol like propane 1-ol, it first forms propanal, but we need to distill it directly, or if we leave it, it will change to the acid. So when we want to collect the aldehyde, we need to use this kind of apparatus, which is simple distillation. A flask with anti-bumping granules, and we heat it. We have a thermometer, a condenser with water going in from down and coming out from the top, and some sort of receiver or flask that we will collect the aldehyde in. So this is simple distillation to obtain the aldehyde. An electric heater may be used to heat a sample of an alcohol with acidified potassium dichromate. So we need to heat alcohol. He's saying state why an electric heater should be used rather than a Bunsen burner to heat these reaction mixtures. Remember that alcohols are flammable. So we shouldn't heat it directly with a Bunsen burner. We shouldn't put it near an open flame, or it will catch fire. So an electric heater would be better since alcohols are flammable. State why there is no reaction when 2-methyl propane 2-ol is heated with acidified potassium dichromate. Can you see why 2-methyl propane 2-ol would not be oxidized by acidified potassium dichromate? Of course, this is because this compound is a tertiary alcohol, so it cannot be oxidized. Remember, the OH is bonded to a carbon that is bonded to 3 other carbons. So this is a tertiary alcohol, and you should know that tertiary alcohols are not oxidized. Identify by name or formula all the possible oxidation products of propane 1-ol and propane 2-ol. Okay, when we oxidize propane 1-ol, that's a primary alcohol. It gives the aldehyde and then the acid. So it would give propanal and then propanoic acid. Propane 2-ol is a secondary alcohol. So when it is oxidized, it gives the ketone. So this gives propanone. The last question says, give a further chemical test and the positive results for each of oxidation products of propane 1-ol. So we said when we oxidize propane 1-ol, we get propanol or we get the acid. So test for the aldehyde, we add Benedict solution, we get a brick red precipitate if an aldehyde is present. The test for acid, if it formed propanoic acid, remember that the test for acid is I should add a carbonate. So add sodium carbonate, for example, this should give bubbles of gas that turn lime water milk. Okay, and that's the end of the paper. I hope you were able to understand the questions, and thank you for listening.